James Webb found a red point of light only about 660 million years after the Big Bang. At first glance, it looked almost like an enormous cool star. Its surrounding glowing region could span roughly the scale of our solar system. But there was a problem. No normal star could produce anything close to the amount of energy coming from it. Researchers estimate that the object is radiating at a level roughly 100 billion times beyond what a conventional star could physically produce. The best explanation is that there is a massive black hole hidden inside. Astronomers call the object MOM BH1, and they argue that it represents something never clearly observed before, a black hole star. It is not a star with a black hole somehow replacing its core in the ordinary stellar sense. Instead, the system appears to contain an actively feeding black hole surrounded by an extremely dense envelope of gas. The black hole provides the energy, while the surrounding gas absorbs and reprocesses that radiation until the entire object begins to resemble a gigantic stellar atmosphere. This discovery could solve one of the biggest mysteries created by the James Webb Space Telescope. Since JWST began looking deep into the early universe, it has repeatedly found compact objects nicknamed little red dots. They were not expected in such numbers. They are extremely red, often surprisingly bright, and many show evidence that something energetic is happening inside them. Yet traditional explanations involving ordinary galaxies, dust, or familiar quasars have struggled to reproduce all of their properties at once. MOM BH1 may finally reveal what at least some of those dots actually are. The object was found during a JWST program called Mirage or Miracle, or MOM. The researchers were originally searching for extremely distant galaxies rather than a new class of object. When they examined this source, however, its spectrum contained an unusually strong feature known as a Balmer break. A Balmer break occurs when hydrogen changes how efficiently it absorbs light across a particular wavelength range. In ordinary astronomy, a strong break can indicate a population of evolved stars. Here, the feature was so extreme that a normal stellar population became difficult to justify. That is exactly what astronomers might expect in the young universe before generations of stars had enough time to manufacture and distribute large amounts of carbon, oxygen, iron, and other heavier elements. The researchers therefore modeled an environment dominated by dense primordial gas surrounding an accreting black hole. The result matched surprisingly well. Their preferred model contains a black hole with a mass of roughly 100,000 suns. Around that black hole lies an enormous cocoon of dense gas, potentially extending across a region comparable to the size of the solar system. Instead of seeing a thin, flat accretion disk around a mostly exposed black hole, as in the simplified picture of a quasar, JWST may be looking at a black hole almost completely buried inside its own fuel supply that changes what the radiation looks like before it escapes. Close to the black hole, in falling gas, releases enormous amounts of gravitational energy. But the surrounding cocoon is so dense that much of that radiation cannot travel directly into space. Photons repeatedly interact with the gas. The energy is absorbed, scattered, and re-emitted until it finally escapes from much farther away. To a distant telescope, the outer gas can behave somewhat like the photosphere of a star. The energy source, however, is not nuclear fusion. It is matter falling toward a black hole. This produces the strange hybrid appearance. The object has a star-like outer envelope, but a black hole engine. And that may explain why astronomers found little red dots so confusing. If researchers interpret their light as coming mainly from stars, they can infer absurdly dense or massive stellar systems. If they interpret them as ordinary quasars, other parts of their spectra often do not fit. A dense gas cocoon around a rapidly feeding black hole can potentially reproduce several of those contradictory properties at the same time. There is another reason this matters. Astronomers already know that supermassive black holes existed surprisingly early. Some quasars seen less than 1 billion years after the Big Bang contain black holes hundreds of millions or even billions of times the mass of the Sun. The difficult part is explaining how they became so large so quickly. A black hole beginning with only a few times the Sun's mass has limited time to grow before these early quasars appear. One proposed solution is to begin with a much heavier seed. Under special conditions, enormous primordial gas clouds might collapse into black holes containing thousands or tens of thousands of solar masses. Another possibility is that smaller black holes experience episodes of extremely rapid growth. A dense black hole star phase could potentially help with both problems by surrounding an early black hole with a vast reservoir of gas and allowing it to grow efficiently. MOMBH1 is particularly interesting because researchers appear to be observing the black hole component almost without interference from a bright surrounding galaxy. In many little red dots, ordinary stars in the host galaxy contribute part of the light. In this object, the black hole star appears to overwhelm its host, giving astronomers a much cleaner view of the central engine. That makes it a kind of missing evolutionary snapshot. Imagine a young black hole buried inside a dense reservoir of primordial gas. At first, radiation struggles to escape. The object appears red and compact. As the black hole grows, radiation, winds, and eventually jets may begin clearing the surrounding material. The cocoon becomes thinner, the central engine becomes more exposed, and the system begins resembling the quasars astronomers already know. Eventually, the host galaxy develops around it, producing the familiar configuration of a supermassive black hole sitting at the center of a large galaxy. The black hole star could represent an early stage in that sequence. Researchers are now asking whether this explanation applies to many of JWST's little red dots rather than only MOMBH1. One 2026 survey identified hundreds of candidates whose rest frame optical light appears dominated by similar black hole star templates, suggesting that these objects may not be rare exceptions. If so, rapid black hole growth inside dense gas envelopes could have been a common phase of early galaxy evolution, but the interpretation is not settled. Other teams have found evidence that some little red dots contain more complicated gas structures than a completely sealed envelope. Observations of one well-studied source at redshift 7.04 revealed ultraviolet emission that appears able to escape from near the black hole, suggesting that the obscuring gas may contain openings or be highly clumpy. That does not necessarily eliminate the black hole star idea, but it means the simplest picture of a perfectly closed spherical cocoon may be incomplete. This distinction is important. MOMBH1 is being interpreted through spectra and physical modeling. Astronomers have not taken a direct photograph showing a black sphere embedded inside a giant red cloud. The object is far too distant for that. Researchers compare the light detected by JWST with different models and ask which physical scenario reproduces the observations most naturally. For now, the gas-enshrouded black hole appears to provide the best explanation for MOMBH1. Future JWST observations should make that test much harder. If black hole stars are real and common, astronomers can search for consistent spectral signatures across larger samples. They can measure how their properties change with cosmic time, estimate their black hole masses, and search for the transition from deeply buried objects to exposed quasars. The result could transform one of JWST's strangest surprises into an evolutionary story. When the telescope first revealed little red dots scattered through early universe images, they looked like an unexplained new population. Some seemed too compact, too bright, or too unusual to fit comfortably into existing categories. MOMBH1 suggests that the problem may have been the categories themselves. It is not quite a star. It is not an ordinary quasar. It may be a young black hole wrapped inside so much gas that the gas becomes its temporary atmosphere. A black hole roughly 100,000 times the mass of the Sun may be hiding inside an object the size of our solar system, shining through primordial hydrogen only a few 100 million years after the universe began. And if the same explanation applies to the countless little red dots, JWST keeps finding. Astronomers may not simply have discovered a strange new object. They may be watching the stage when the first massive black holes were being built.